Hello, this is question 4 from the 2014 Matt. In the diagram below is sketch a semicircle, centre B, radius 1. Okay, let's mark on some of these. Actually, there's so many lines on here, but I'll put a 1 there and there. No, there's another one going from DB. Actually, I will put it on. Okay, but that's going through all the way from B to D. It's got nothing to do with X. 3 points ACD lie on the semicircle as shown with alpha denoting the angle CAB. CAB, yeah. Beta denoting angle DAB, DAB, yeah. Triangles ABC, ABD intersect in a triangle ABX. So, okay. Throughout the question, we shall consider the value of alpha fixed. Right, assume that, right, so alpha's fixed. That's important, I would imagine. Assume for now that alpha is less than or equal to beta and beta is, well, alpha's fixed, so beta's varying then. That's what they're suggesting, between alpha and pi by 2. So we've got D is moving between C and A. It can go as far as C and it can go round to A. So we've got that option for changing our beta angle. Right, show that the area of the triangle ABC equals that. Right, okay, so ABC is isosceles. Well, so's ABD as well. So let's put those on. Let's get more things on the picture. That's a beta, that's an alpha, because they both got radius, 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 radius. So we've got those isosceles triangles. So the area of ABC is, we're going to do a half AB times C. So we're going to have a half times 1 times 1 times sine of that angle. So it's going to be a half of the sine of pi minus 2 alpha, which for sine means a half of the sine of 2 alpha, which is what they want. So that was a nice starter. Let F be the ratio of the areas of triangle ABX and ABC. Without calculation, explain why for every K in the range 0 to 1, there is a unique value of beta such that F is equal to K. So F is, okay, so it's going from 0 up to 1 is what we're saying. So there's some value. So when, well, D we know is moving. It must be to do with this. So when D is on C, then we've got the two triangles are the same. Oh yeah, when D is on C, X is at C as well. Okay, so how are we going to put this then? So D can move from C to A along the semicircle, which changes beta from alpha up to, well, it will end up being tangent there, wouldn't it? So up to pi by 2. That's the full range of beta that we've got there. Okay, so then we can say when D is at C, then we've got F equals 1. When D is at A, we've got that F is equal to 0. So that's okay. So actually I'll just put there in that one because X is at C. And then here, because X is at A, when we move those all the way round. Okay, so what am I going to say? Without explain why for every K in the range K is 0 to 1, there's a unique value of beta. Right, so as D moves from C to A, F decreases from 1 to 0. 1 to 0. Okay, there is a unique value of beta. Yeah, and each I don't know, what word am I trying to use here? As D moves, beta is varying. That's what I wanted to say. So as D moves from C to A, F decreases from 1 to 0 as beta increases from alpha to pi over 2. Right, so yeah, I mean, that is it really, isn't it? Without calculation, explain why for every k in the range 0 to 1, there's a unique value of beta such that f equals k. Right, they're just confusing things really by putting this k in. So f is varying between 0 and 1 as d is moving round. So let's just see if that makes sense from what I've said. D can move from C to A along the semicircle, which changes beta from alpha to pi by 2. When D is at C, F is 1. When D is at A, F is 0. As D moves from C to A, F decreases from 0 to 1 as beta increases from alpha to pi by 2. Therefore, each value of F, let's just finish with a statement, from 0 to 1 will have a unique value of beta. Right, okay, that was quite nice. Okay, part 3, find the value of beta such that f is a half. So the area of triangle ABX is half that of the area of ABC. Right, so as D's moving round, yeah, we're going to end up, well, we're going to end up actually just splitting that straight down the middle, aren't we? We're going to get a right angle there because this thing's isosceles. And we're going to have x right there. And then, yeah, well, that's going to be it, split in half. Right, so how do we then get, let's have a closer look at that picture then for 3 of what we've got. So we've got a triangle, we've got, this is our ABC, which is looking like that. And then we've got a perpendicular going through there up to D and then coming down here. That's a right angle. That's our alpha. That's an alpha. That's our beta. And that's a beta. Okay, so with all this set up, let's fill in more angles then. So this angle here, well, and that angle there, are both going to be pi over 2 minus alpha. And it's also going to be pi minus 2 beta. Okay, right, so that's going to help matters considerably, because now off of that we can just do that 2 beta is pi over 2 plus alpha. So beta is pi over 4 plus alpha over 2. Okay, right, so that dropped out okay. I need a new sheet. New sheet. Show that f is equal to that. Right, that's a bit annoying, isn't it? Now we're doing this just generally. Well, we know the area of ABC, so let's start with things, you know, that we know all about. So ABC, we were saying, was a half sine to alpha. So that's got us our sine to alpha bit in the answer. And the halves of that half has gone away, so it suggests we're going to be doing another half AB sine C for our ABX. So let's look at X then. And oh, we got betas in this as well, so we could do it off of, and we got that angle there, which we know is, that was our pi minus 2 beta, that angle. So we could work off of that. Or we could, because we've only got one side at the moment, haven't we? We've got that length 1 there, so actually we're going to have to do sine rule as well. We can't just do this just off of, well, let's set that length to be x, go from A to X. So let length AX equal X. So then we've got the area of area ABX. Now we have our half times A, which is 1, times B, which is x, times sine alpha. So, okay, we've still got this x that obviously we don't have in the answer. So we've got to get rid of that, and we can get rid of that using the sine rule. So let's do our f first of all. So we're doing ABX divided by this. So we've got x sine alpha divided by sine 2 alpha. Okay, so we've got the sine alpha, we've got the sine 2 alpha. So we're hoping that x is going to come out as that. So, and yeah, this is going to fit with doing sine rule stuff, isn't it? So what have we got on all of this then? So we will have an angle, well, we've got x over sine pi minus 2 beta is just then going to be sine of 2 beta. So we've got that, x divided by that. And then we're going to have 1 divided by, we've got this annoying angle over here. But that is then the sine of, good grief, so it's pi minus 2 beta minus alpha. Right, so the pi's cancel, and that is then sine of 2 beta minus alpha. Oh, okay, what do we know? So there we go. X is sine 2 beta over sine of 2 beta minus alpha. And then we plot that x into here, and we've got exactly what they want. Right, that's fine. Right, that looked as though it was going to be a little bit more unpleasant, but there wasn't really any other way we could go about it, I don't think, other than doing that. I mean, you just have to piece together these triangles as they come. This is often the way with geometry questions, isn't it? That you just fill in bits as you go along. If you don't know what something is, just give it a letter and see if it works itself out further down the line. But this one's all about the angles. It's because we've got these two isosceles triangles. It makes things so much easier. Right, part 5, last part. Suppose now that beta is between 0 and alpha and all less than pi by 2. Right, so alpha is fixed. Yes, this is what we, okay, it was on the previous slide, but that's what they stressed at the beginning. So alpha's fixed, beta's now moving on the other side. So we've moved D over to here from C to then down to this unnamed point over here. Let's call that E. Write down without further calculation an expression for the area of ABX and hence the formula for F. So, right, what's happened to ABX then? Let's do a little, because that picture's a bit messy. So ABC hasn't changed. That's still sitting there with our alpha and our alpha. D's now on the other side. So go over here to D off of there. And that's coming round. That's our D. That's our beta. That is our beta. So the calculations then, so what's our ABX is now going for, is these bits. That's our X. So ABX. Right, so all the calculations we did before then, what has changed for ABX? So before, for ABX, we had this sort of setup where we had an angle alpha, we had an angle pi minus 2 beta, and we had that angle there, which we were saying is pi minus both of these things. So pi minus that, so that was our 2 beta minus alpha. Right, so that's the 3 angles that we had there. Now we've got a triangle which looks like that, which has got a beta there. This angle here, what angle is that going to be? So that's now going to be pi minus 2 alpha. And then this angle is going to be then 2 alpha minus beta. So we flipped around all of the alphas and betas for that triangle. So we just need to go to our area for ABX. So ABX now is going to be, so that's this thing with that thing put in it. So, right, okay, so it's now, so X, write this thing out. So sine of 2 alpha then multiply by sine alpha, this one up here, and then divide by 2. Oh no, that'd be a sine beta because we flipped them. God, I need to make sure. I'm going to have to double check this after I've written it out. And then the denominator, we've got the 2 sine 2 alpha minus beta. Yeah, that's going to work, isn't it? So we've got the sine 2 beta, that one has become sine 2 alpha, that one. The sine alpha has become the sine beta. And the sine 2 beta minus alpha has become sine 2 alpha minus beta. Okay, hence a formula for f. But ABC hasn't changed because C is fixed. So that hasn't changed. So f, ABC is still this. So, and the halves are still going to cancel. So we're doing all of this thing without the 2. So this 2 goes away. Oh, and we're going to cancel the 2 sine 2 alpha as well. So we're going to get sine beta divided by sine 2 alpha minus beta. Okay. Yeah, that's all just about drawing out the picture, right? To squeeze it on a little bit here, as usual, with it being on the screen. But if you draw out the original A, B, X and mark on the angles, and then draw out the new A, B, X, and then mark on the angles, and you can see what's changed quite easily there when you flip from one to the other. That was a really, really nice question, that one. Again, geometry bias. But yeah, I thought that one was great. Really pieces things together nicely. And it's another one of those ones as well, visualizing these pictures when you've got moving parts. Yeah, don't just look at this as a static picture. Look at this as having D moving around. As soon as you see this, and they've told you that alpha is fixed, beta's not fixed, think, okay, well, what's happening as beta is moving between alpha and pi by 2? D is skirting around the edge of the circle. So look at that picture as being an animation rather than just being a static picture. Really brings the whole thing to life, and you can start seeing what's actually happening. So yeah, that is a great question.